Thank you. Good morning or good afternoon, everyone. So I'm Nuria Oliver, and I'm going to be sharing with you for the next 40 minutes or so the experience that we've had the Valencian region of Spain in using data and AI to help fight COVID-19. The main goal for this team that I have led between March of 2020 and April of 2022 is to assist in better decision-making and policy-making during the pandemic through the analysis of data using machine learning and AI-related algorithms. We are a multidisciplinary, multi-institutional team located in the Valencian region of Spain, which is on the east part of Spain on the Mediterranean coast. And you can see here the different universities, research centers, and scientists that have been working with me on this task. The main goal for our task force has been to fill the gap between where data is and where the policymakers are. If we would like the decisions and the policies to be based on evidence, and if we believe that data is a digital representation of an underlying reality, then the challenge is to connect the data with the policymakers and the decision makers. In the context of the COVID-19 pandemic, we have structured our work in 4 areas. The first one is human mobility analysis, because obviously disease that is transmitted from human to human, like COVID-19, doesn't become a pandemic if people don't move and spread geographically the disease. So quantifying and understanding large-scale human mobility is very important in the context of pandemics. The second work stream has focused on building computational epidemiological models, models that would enable us to predict the number of COVID-19 cases, not only under the current situation, but also under different possible scenarios of different measures of confinement. The third area has focused on building predictive models, mostly of hospital occupancy, intensive care occupancy, and also inferring the prevalence of the disease. And last but not least, we have launched a large-scale citizen survey called the COVID-19 Impact Survey, which with over 720,000 answers is one of the largest citizen surveys about COVID-19. Even with all this work, there is still a gap between the output of all these areas and where the policymakers are. And I think one of the key elements for the success of our team has been the existence of this layer here of results interpretation, aggregation, and preparation that was mainly done by a policymaker, the Director General of Public Policies working in the presidency of the Valencian government, together with me, to really identify the most important findings and translate them into actionable political language, and also to help us prioritize key questions to address with our analysis. In terms of the expertise, everyone was a scientist, from students and sort of a very junior to full professors and very senior researchers. And depending on the area, there were slightly different areas of expertise. So the mobile data team had a lot of expertise, obviously, on sort of like GIS data analysis, also data wrangling and visualization. The epidemiological team had a lot of background in machine learning and computer modeling. The predictive models teams also had a lot of background in machine learning, and the citizen science team had additional background in sort of like user studies. We worked really intensely for many months. We met daily. I organized daily meetings, and I also wrote daily reports with the predictions of the day and some of the recommendations of the day. We had a common GitHub repository, a very active Slack channel with many sub-channels, and of course everyone signed the necessary legal paperwork to be able to work on this project. This is an example of one of our daily meetings, and we also have an official website, the Valencian government's website. Creating such a team is actually not easy, and that's probably why there aren't a lot of examples like our team in other places in the world. Some of the challenges entail the fact that most public administrations and governments still don't have a lot of digital capacities, awareness, and sort of like mindset. And they don't have a lot of like profiles that we have, like data scientists, for example. There are also difficulties related to accessing the right data, concerns about privacy and data protection, especially at the beginning, in the early days, in March of 2020, April, and May of 2020, we had a lot of interactions with the data protection officer in the government, but also all the data that we analyzed and that we'll share today was aggregated, anonymized, and mostly publicly available data. There is a gap between where the research projects are and where the real world is, in a sense, and filling that gap is non-trivial. And also, of course, if we don't have all these elements in place when a pandemic starts, you need to immediately react and immediately leverage all these elements. And if they are not there, it's very difficult to build them, on the fly. We actually a team of scientists from all over the world with a lot of expertise on using data to help fight pandemics. We wrote this paper that we published in Science Advances, where we present ideas on how mobile phone data could help in the context of the COVID-19 pandemic. So what have we done? So I'll quickly go over some of the results in each of the different areas. In terms of the human mobility analysis, the main purpose is to quantify and model human mobility to be able to determine to which degree the confinement measures were working, to identify areas where they might not be working, to determine the types of mobility that had been the most impacted by the confinement measures, and to also assess the impact of such confinement measures on the progression of the disease. We were appointed by Vice President Calviño in March of 2020, the pilot region in Spain, to be able to analyze large-scale anonymized human mobility data that was obtained or that was created by the Spanish National Office of Statistics from data that was shared by the 3 largest telcos in Spain. This is a visualization of the data in the Valencian region of Spain in March of 2020. You can see the 4 largest urban areas in the region: Castellón, Valencia, Alicante, and Elche, and you can see some of the mobility that was taking place. One of the analysis that we did was trying to assess the impact of the stay-at-home campaign. Early in the pandemic, during the first wave of infections, Spain underwent a very severe confinement, and one of the objectives was to persuade the population to stay at home. With this data, we don't have the spatial granularity to determine the specific home of any individual, obviously, but we have this concept of the area of residence, which you can see depicted on the map, where an area of residence is a geographic area where people spend the nights, and for privacy reasons is large enough to have at least 5,000 people in it. In the map, we are showing the percentage of the population that never left their area of residence for more than 2 hours during, in this case, is during one particular day in the first wave of the pandemic. But if we look at the overall statistics during the first wave of COVID-19 in 2020, we observed that on average, 88% of the population in working days and 92% of the population in the weekends didn't leave their area of residence for more than 2 hours during the strongest and also most stressful period of the pandemic in Spain, which was like the first wave of infections. Here is a visualization of the same map every day during this very severe first confinement. We can see that at the beginning of the pandemic, there was definitely more mobility as the map is yellower and more orange, which means that a smaller percentage of the population stayed in the area of residence. We also observed that Sundays are the greenest days, that is the days where most of the population didn't leave their area of residence. And then we also observed that the first week of April, when there was a very severe confinement in Spain and there wasn't any labor mobility, the map, even during the week, becomes a lot greener than before this severe confinement. To support policy making, this spatial granularity might not be particularly meaningful, so we also perform all the analysis using as our region of reference the departments of health. In the Valencian region, there are 24 departments of health, and a department of health is the geographic region that is served by one hospital, by one large hospital. In this graph, we see the percentage of the population that didn't leave their area of residence during weekdays in reddish color, or during the weekends in more brownish color, in each department of health. And we can see that in all of them, over 80% of the population didn't leave their area of residence in those departments of health. And we can also see how during weekends there is lower mobility than during the week. We also analyzed the labor mobility, and to do that, we compared the percentage of people that spend the working hours outside of their area of residence with the same percentage on a period that was before the pandemic. And we had as a reference period November of 2019. And the map shows the drop in labor mobility when compared to this reference period in November of 2019. And we see that on average, there were 60% less people outside of their area of residence during working hours than during the reference period. To support the use of this data, we developed also an intuitive visualization that was accessible to anyone, where you could click any municipality and any time period, and you could see the incoming mobility, the outgoing mobility, the percentage of people that stayed at home, the labor mobility, and so forth. Given that we had the flows of mobility between different areas, we could also run a community detection algorithm and identify what we call the mobility communities. A mobility community is a geographic region that has a lot of inner mobility, but doesn't have a lot of mobility with other regions. By performing such an analysis, we identified 14 macro zones or mobility communities, and some of them were extremely self-contained, like the first one that you see here, which had 94% of internal mobility. The second area is the area of building computational epidemiological models, models that would enable us to predict the number of COVID-19 cases in the future, not only under the current scenario, but also when considering different potential non-pharmaceutical interventions or confinement measures. The first type of model that we built is a SAIR metapopulation compartmental model. This is a traditional computational epidemiological model which divides the population into different metapopulations that are in different states. And the states are according to the name, which is an acronym, SAIR. So initially, the entire population, which in the Valencian region is 5 million people, is in a susceptible state because COVID-19 or SARS-CoV-2 is a new disease, and we assume that everyone was susceptible of getting it. With a certain probability beta, a fraction of the population is exposed to the disease, so a portion of the population moves into the exposed state. With a certain probability, those that are exposed get infected and infectious, and then with a certain probability, they recover or they die, so they are retired from the system. Early on in the pandemic, the different parameters for this system had been estimated for COVID-19, and we took them as the starting point. The dynamics of this system is given by this set of differential equations, and then we fine-tuned the parameters so they would actually properly fit the data in the Valencian region. We also included mobility into this model, given that we had the information about the mobility. Here I show the temporal evolution of the predictions in red versus the ground truth in dashed. The second type of model that we built is an agent-based epidemiological model. In this case, we model each individual in the region, so 5 million agents. The agents have their own demographic information, gender and age, and a contact matrix that determines how social they are. And they can also be in the different epidemiological states. We based our agent-based model on the REINA framework, and we sort of like created an instantiation for the Valencian region of Spain. Using this model, we also run daily simulations to predict the number of COVID-19 cases, deaths, hospitalizations, and intensive care unit occupancy. And last but not least, in November of 2020, we decided to participate in the XPRIZE Pandemic Response Challenge, sponsored by Cognizant. And a subset of the larger team, we created the Valencia IF for COVID-19 team and participated in this competition. This was a global competition on how data and AI could help tackle this pandemic. The first challenge in the competition entailed building computational epidemiological models to predict the number of COVID-19 cases in 236 regions and countries in the world, up to 180 days into the future, and considering the different NPIs or non-pharmaceutical interventions that were applied in each of these different regions and countries in the world. For the challenge, we opted for a deep learning based model, and we actually built bank of LSTMs, which is a type of recurrent neural networks, and we had two chains of LSTMs, the top one which models the number of COVID-19 cases, and the bottom one which models the influence of the non-pharmaceutical interventions on the number of cases. We had a bank of LSTMs to model the number of COVID-19 cases to allow for the diversity of dynamics all over the world. So we clustered the countries in the world depending on the dynamics of the COVID-19 cases, and then we built different LSTMs for the different clusters. The predictive performance was pretty good during the competition. I think on average it was the third on the mean rank and the first on the European and Asian countries. But more importantly, we finished this model in December of 2020, and the Valencian region underwent the most severe wave of COVID-19 cases after Christmas of 2020 to 2021. And this is what is depicted on the top of these graphs. In yellow, you see the ground truth, the number of cases. In blue, you see the predictions of our model. And in red, you see the predictions of another state-of-the-art model. So as you can see, our model was quite accurate in predicting the third wave of infections. Throughout 2021, we continued working on this model, and we included vaccination. And on the bottom, you see the predictions of our model during the sixth wave of infections, which took place right after Christmas between 2021 and 2022. And in yellow is the ground truth, in red is the predictions of our model, and in green is the predictions of a state-of-the-art model. And again, our model was quite accurate in predicting the sixth wave of infections. The second challenge in the XPRIZE competition require us to develop this pink layer in our architecture, a prescriptor of intervention policies, a system that would, for any country and region in the world, and for any time period, it would actually recommend up to 10 potential policies of non-pharmaceutical interventions that would have the best trade-off between the cost of applying such interventions and the number of COVID-19 cases that would result if you were to apply those interventions. To do that, we developed two different methodologies, which we combined. It was a multi-objective optimization problem, and what we had to do was to find the Pareto front of solutions in this two-dimensional space, where on the one axis there was the cost of the interventions, and on the other axis there was the number of cases that you would have, because there were 12 different kinds of non-pharmaceutical interventions that could be applied. There were around 8 million different possibilities of policies that you could apply, and we had to come up with the 10 optimal policies for the 236 countries and regions in the world for any time period that we didn't know. So we also built a visualization of our intervention recommendation system. You could click on any country, and then it would show you all the different policies on this two-dimensional space. And you could see very clearly the trade-off between the cost and the number of cases. And then at the bottom, you could see the regime of these interventions, which NPIs were active, and with which level of intensity. This was our solution that we presented to the X Prize competition, and we ended up being like the world winners of the competition. So we were extremely happy about this result that really, in a sense, validated all the work that we had been doing for many months prior, over a year, almost a year prior, working on trying to help fight the pandemic. And I think it's actually the first time that a Spanish team was winning an X Prize competition. We also extensively described our solutions in this paper that we presented in ECML PKDD 2021, and we actually won Best Applied Data Science Award, and we are also presenting the paper in HCAI, ECAI in Vienna. One of the analyses that we did after the first wave of infections was the impact of contact tracing. TTI, meaning test, trace, isolate, is the main COVID-19 control strategy that was applied in most countries in the world. And the idea was to test all the suspect cases, trace all the contacts of the positive cases, and isolate all the positive cases to try to prevent community transmission. So we did analysis on the impact of contact tracing, and we found that according to our models, it wasn't necessarily needed to contact trace 100% of the cases, but we were assuming that every positive case would be able to self-isolate, something that we knew that it was probably not the case. And as I said earlier, we also worked throughout 2021 in expanding our models to include vaccination, so we could continue making predictions on the number of cases. And here are some of the predictions on the agent-based model and the LSTM deep neural networks-based model, including the vaccinations, and they actually work pretty well. The third area is focused on building predictive models, particularly predictive models of the hospital occupancy, because of course, for policymaking, one of the key questions was, how many beds are going to be needed, how many intensive care units are going to be occupied. We use different approaches to make these predictions, including a spatial temporal modeling approach, and also we use LSTMs in some of our models. And here in this graph, you see the predictions of the LSTM model on the number of on the percentage of occupancy of intensive care units throughout time. And last but not least, we developed and launched a really large-scale anonymous citizen survey. The reason why we launched this survey, called the COVID-19 Impact Survey, is because in March of 2020, we had so many questions that we couldn't really answer because we didn't have the right data sources to answer them. For example, what is the social contact behavior of the population during the pandemic? What is the economic, labor, and psychological impact of the pandemic on people's lives? What's the prevalence of symptoms? Can we infer the prevalence of the disease from the prevalence of symptoms? What are the individual protection measures that people are taking? Are there enough tests for everyone? How resilient are people to face all these difficulties during the pandemic? Is contact tracing working? I mean, we had a lot of questions. So invested a fair amount of effort very early on in the pandemic to design the shortest possible, most informative possible survey that we could launch and that could help us answer these questions. And this led to the COVID-19 Impact Survey, which originally had 26 questions and which was launched on the 20th of March of 2020. The survey has been translated to many languages, and we have really large data sets of answers from Spain, and then a smaller size, but fairly large as well, from Italy, Germany, and Brazil. The survey was very well received, and in the first 40 hours, we received, I think, over 140,000 answers, and that really indicated to us that people were very eager to help, and also that the survey was giving people a voice to communicate how they were doing. And we felt a responsibility to share as quickly as possible the results of such an analysis. So we very quickly analyzed the data from the first week of deployment, and we shared it online so it will be available to anyone. We also provided 10 key conclusions of the analysis that actually applied later on for the entire time of the pandemic, except perhaps the finding that more tests are needed, because at the beginning of the pandemic there weren't enough tests, but then tests became widely available. We deployed 2 different visualizations for the survey, and the one that we've been keeping updating throughout the pandemic is the one on the right. And anyone could access it, citizens, the media, politicians, to understand what was the situation of the population at that particular moment in time. We've also written several scientific papers where we delve more in depth into some elements of the answers of the survey. And I just wanted to share with you some of these findings. The first one concerns the emotional impact of the pandemic. And what we have found is that systematically throughout the pandemic, the most impacted demographic group is the youth. Here you see the 3 age ranges: 18 to 29 years old, 30 to 59, and 60 plus. It is divided by gender. In blue, we have the male answers, and in reddish, we have the female answers. And we can see that it is the 18 to 29, the ones that have the highest percentages of impact. When we look at the stress levels, over 50% of the women aged 18 to 29 report stress levels that they consider detrimental to their health. Even loneliness, which perhaps is a surprising result, was the highest among the youth. Another interesting area is the perception of the population of the government measures. This graph shows the evolution of such a perception throughout the pandemic. In yellow, we see the percentage of respondents that consider that more should be done. In green, those that considered that the measures were enough. And in red, the ones that considered that the measures were too much. And as you can see, the most popular answer throughout the pandemic has been that the government should do more. And there is a very high correlation between the increase in the percentage of people considering that more should be done and a wave, the existence of a wave of COVID-19 cases. When we look at the individual protection measures, this is recent results, but when we look at the overall evolution throughout the pandemic, we find that women have been systematically more compliant with individual protection measures when compared to men. We also find that the most popular measures in Spain were disinfecting hands and wearing masks. We had a mask mandate throughout the pandemic, and the mask wearing percentages were really high. These percentages are lower because the measures were a lot more relaxed in the later stages of the pandemic. And perhaps one interesting finding is that the least adopted measure was ensuring indoor ventilation, despite the importance of indoor ventilation to help prevent the spread of the virus. And finally, Spain has a very, very high intentionality to get vaccinated. These percentages are actually lower than have been in earlier stages of the pandemic, because at this point in time, 90-something% of the Spanish population was already vaccinated, but still the intention to get vaccinated in Spain has been extremely high throughout the entire pandemic. We also see a differential perception of risk of different activities. In this graph, it shows the evolution over time of how likely people thought, or how safe people thought that different activities were in terms of the risk of getting COVID-19. We see that the safest activity throughout the entire pandemic has been doing sports individually outdoors, which seems to make sense. If you are alone and you're outdoors, it's probably not very likely that you will get COVID-19. And the least safe activity throughout the entire pandemic has been flying by plane, even though there aren't a lot of recorded outbreaks happening in planes. Some activities have dramatically changed in their perception of risk depending on the time period, and one of them is going to the beach, which is marked in red. As we can see, in the winter months, fewer people think that it's safe going to the beach, but then as the summer comes and people start going to the beach, the perception of risk goes down and is considered to be a safe activity. We also monitor throughout the entire pandemic the ability of people to self-isolate. The isolation is the last pillar in the TTI control strategy. We first observed that roughly 50% of those aged 59 and younger are actually reported not being able to self-isolate if it was necessary during the pandemic. We also observed gender and age differences. The first finding is concerns the psychological challenges. Throughout the pandemic, it is the youth, those aged 18 to 29, the ones that report not being able to self-isolate because of psychological reasons or fear of stigmatization, with a lot higher probability than any other demographic group. We also observe gender differences, and we can see here highlighted the percentage of respondents that say that they couldn't self-isolate because of having to take care of their children. And as you can see, the women who are at the bottom are a lot more likely to report not being able to self-isolate because of taking care of children when compared to men of the same age range. And finally, we studied the impact of the digital contact tracing app. And this is an example from Spanish data. So when we take a pool of around 140,000 respondents, we find that roughly 30% of them reported having the app installed, which is a fairly high adoption rate. That would be 42,000 people. Of those 42,000 people, 7.7% reported having had a close contact with an infected individual. Of those, 86 reported having discovered it via the app, which will be 2.6%. Only 27 of those 86 got tested, and only 7 tested positive. So from an initial pool of almost 140,000 people, the app in this particular case helped identify 7 positive cases. And the last analysis that we've done more recently is about social isolation. We are concerned that the isolation that we have been undergoing throughout the pandemic could have had important implications in terms of the isolation levels of the population. So in June of 2021, we added 6 questions to the survey, which is the Lubin self-isolation 6-item scale, to assess the levels of isolation in the population. And we just published this paper a couple of months ago, where we report quite worrisome results in terms of the prevalence of self-isolation in the Spanish population, being out of a sample of over 32,000 answers, having a prevalence of almost 26% in the overall population, but as you can see here, reaching 30% among those that are middle-aged, between 40 and 59 years old. We also find a strong impact in the probability of being self-isolated among those that had severe economic or psychological impact because of the pandemic. So what have we learned after 2 years and all this work? The first lesson, which is the most obvious lesson, is that pandemic is not just a public health issue. It is a societal challenge that requires multidisciplinary, multi-institutional, holistic approaches. We have also learned that there is an opportunity to create a virtuous cycle between these 3 elements. First of all, data that will be systematically captured and analyzed so we can understand where we are, why we are where we are, and also predict where we might be going. Secondly, people and technology, the right amount of human resources in all these different fields, the healthcare and social personnel, contact tracers, teachers, researchers, but also empower with the right data and the right technology so they can really do their work productively. And ultimately, we want to leverage all the findings and all the learnings from all these data analysis to inform the design of processes and public policies, so they would really address potential weaknesses or limitations in society. For example, if we know that the youth is the most impacted demographic group in terms of psychological impact, it would make sense to deploy mental health support programs for the youth. Or if we know that young people have difficulties to self-isolate, if they have young children, or even younger people have difficulties because of psychological reasons, then we could deploy programs to support self-isolation. We reflect on the opportunities and the challenges that data and technology offer in the context of the pandemic in this publicly available report that we wrote in collaboration with DataPub Alliance and the Vodafone Institute, and where we also put forward 6 recommendations thinking about, that they could be helpful in the case that there are future pandemics. We have also published a lot of papers that are publicly available in case you would like to know more about our work. And we have published, we have given a lot of talks and been very extensively covered in the media. There is this Wire article, How Valencia Crashed COVID with AI, that summarizes our story, and that could be interesting to you. And this is all I had to share with you today. So thank you very much for your attention, and I hope that you found my talk useful and interesting.
Thank you for speaking.
I don't know if there are any questions.
Yeah. Thank you for speaking. We're grateful to those who attended this session, and we'll now start our short survey that helps us shape future conferences. Thank you. And in case you want to reply to questions like here,
I don't know where the questions are.
So you're welcome.
But I don't see the questions. I don't know where they are.
I've seen I've seen 2 of them in liveodsc.com in a channel.
Maybe you can read the question to me, and I don't have the questions in front of me.
So the first one is about the slides which were shared, if the attendee can get them. And the second one was, how do you think your research model will impact future global health emergencies?
Yeah, so that's a very good question. We are hoping that to have contributed to some degree to help push the state of the art and help be better prepared for future public health emergencies. But beyond the specifics of the work that we have done, I think the pandemic has served as a catalyzer to really accelerate the necessary digitization of the public administrations. So I do believe that as a result of the pandemic, a lot of the governments and public administrations in many countries in the world have really taken a lot more seriously and have embarked in digitization and modernization processes. So next time, they'll be able to leverage data in a much easier way to support their decision making and also to evaluate the impact of their decisions in the real world. Based on the data you have seen, do you think any public health decisions were driven by political decisions or data-driven decisions? So and that's a very good question, which is sort of what's the weight of political elements versus evidence, I guess, driven elements. I think we have learned that public policy making is an extremely complex process where our work and our recommendations and our results were definitely a key input to the system. But of course, as I mentioned at the end of my presentation, pandemic is not just a public health challenge, it's an entire societal challenge. So in addition to our task force, data science task force, there was an additional advisory team to the president, which was extremely multidisciplinary, and it had experts from all the disciplines: history, economy, psychiatry, sociology, of course, epidemiology, public health. And we met, I think, weekly for many months to provide this really diverse perspective on the impact of the pandemic and what some of the priorities could be. And I think combining all these different inputs together with other political information is sort of like how the decisions were made, in addition to mandates that could be coming from the European Commission or from the Spanish federal government. So I think I think the decision making was complex, but I do feel that our work was very much taking into consideration and respected, and I think that was already a nice achievement. For your locally adopted models around Valencia, I'm interested to know how you made the decision of where to do the geographic cut. I guess he means around the Valencian city, the city of Valencia. So the predictions of the COVID-19 cases, we did them either at the level of the Department of Health, which was well defined. There were these 24 departments of health, or at the level of the province or the level of the entire region of Valencia. So that's how we had the geographic regions that we did. And for the X Prize competition, I don't think Spain was divided into any region. I think it was just Spain. The regions that were used in the X Prize competition were, for example, the 50 US states or the 4, I guess, kingdoms in the United Kingdom, but the 17 Spanish autonomous regions were not part of the X Prize competition. It was Spain as a whole. All right, well, enjoy the rest of the conference.